We can start, and now we are live again. So thank you everybody for joining for the first keynote talk that we have in today's agenda. It's really my pleasure and an honor to introduce Octavia. Octavia is a really well-established professor in the Northeastern University in US. She's a Latin. She's actually from Uruguay. It's the first time that I meet her, and I'm really nervous to introduce her because in her profile you can find like all the amazing things that she has done over the course of her career since since the 90s. So you can imagine like all the things that she has done for the computer vision community. And I think that that's also like an opportunity to tell her thank you, because thanks to you, for sure you have inspired others to do computer vision. So I think that in today's talk, I'm really looking forward to it because she will be talking about video representations, which is a topic close.
Oh, I think we froze, no?
Yeah, I lost Victor's.
Yeah.
Victor, thanks again for inviting me and for organizing this workshop. It's really an honor to be here. I'm going to be presenting work that I have done with my students, Armand, Haolin, Wenxian, Dan, and Risi, and my postdoc, Sandesh, and my collaborator, Marius Nair. So I should say also that Armand is from Spain and Mario is from Uruguay as well. So there's a couple of Latin people in this group. So anyway, I wanted to talk about a topic that's dear to my heart, which is video-based representations using dynamics. And it's something that I have been working for several years now. And I wanted to present an overview of the last things that we have been doing in our group. So we do this kind of thing every day. We cross the street and we look for a gap in traffic. Sometimes we do jaywalking, and we do this without too much fear of dying run over by a car, because we know that by looking at things, we can make predictions and figure out whether we will have enough time to cross to the other side of the street. And that happens not in the very least because we live in a casual world where we can make predictions in the future based on the past. So this causality, the fact that we can predict the future based on the past, is key to the things I'm going to be presenting today. We can use my slide is not advancing for some reason. There. We can use temporal sequences to perform inference. We can do things like predicting the future. We can do classification. We can do imputation with missing data, and we can clean noise and detect anomalies and outliers. Today, I'm going to be talking mostly about the first three, prediction, classification, and imputation, but anomaly detection is also something that we have worked in the past. So the main tool that I'm going to be using today to describe these techniques is by doing representations of temporal sequences based on dynamics. So the idea is that given a temporal signal, y of k, like here, can you see my mouse when I move?
Yes, yes.
Okay, yes. So we're going to represent this signal as the output of a linear time invariant system in the most simplest case. But sometimes we are going to also switch between different linear time invariant systems so we can model more complex signals. And sometimes we're going to put also nonlinearities at the input and the output. Of course, these nonlinearities are going to be neural networks in our cases. So I'm going to show cases where each of these representations have become useful for us. So let me first start by the simplest one, where we're going to model a signal as the output of a linear time invariant system. And we're going to use that to design an autoencoder that is aware of dynamics. So we call this encoder DYAN for Dynamic Atomic Network. And as I'm going to show next, we're going to do is build encoder and decoder in order to model these signals as the output of an LTI system. The main idea is like this. If we look at temporal signal like this one here, we're going to model this as the output of an LTI system. Here I have a cartoon that says that this signal came out of a system that has 3 poles in the complex plane, 1 real pole and a pair of conjugate poles. Now, when we look at the transfer function of this signal in the Z domain, we see that really the signal can be expressed as a linear combination of impulse responses of simple systems, systems that have either 1 pole or 2 poles. For example, if we have complex poles, it needs to have 2 because it needs to have the conjugates. So pictorially, what I'm saying is that this signal that was created by a system that has 3 poles here can be expressed as the superposition of the signal created by a pair of conjugate poles and a real pole. And therefore, we can use the coefficients of the combination, of the linear combination, and the poles of the subsystems that I'm using for doing the combination as an encoding of the input signal that we were given. Moreover, the number of poles that we need to use is what we call is the memory of the system. And of course, the simpler the dynamics, the least memory that we're going to need. So we want in general to seek representations that has this n number as small as possible. We want to be able to model our signal with as few systems as we can. So here now is how the autoencoder is going to work. So you give me a sequence of temporal data. For example, it could be a video, or it could be the sequence of the joints of a skeleton. And we're going to try to encode that with this encoder. Okay, so to do that, what we're going to do is we're going to build a dictionary of atoms. And these atoms are dynamical based, and they have physical interpretation. So we have in this matrix over here, per column over here, we have the input response of dynamical systems that are modeled with either 1 or 2 poles. And because these poles in general are complex, they have a real part and imaginary part, the input response. So what we're doing here, instead of working with complex numbers, the columns are going to have the real part of the impulse response and the imaginary part of the impulse response. The good thing is that this dictionary has a physical interpretation. These poles, for example, if we look at a system that's described with a pole at 1, we know that it describes a constant sequence. If we have a pole that has a magnitude greater than 1, then it's an unstable pole and the signal is going to be increasing. If we are at the circle, we're going to be modeling a periodic signal. So it's very easy to understand, if we know what poles we're using, what are the components that are making up my input signal. So now that I have this dictionary, what we want to do is to create a set of latent features, which is sparse. And the idea is that I want to be able to recover my input signal Y by multiplying this sparse feature C times the structure dictionary that I just explained. And so we're going to solve this optimization problem where we want to have as few poles as possible. So we're going to have this sparsity term here. And as well, we want to have very good reconstruction. So we want this fidelity term to be small. So the sparse features over here in the latent space is a solution of this lasso problem minimization. Once we have this C star, then we can reconstruct the input signal by just simply multiplying C star with the dictionary. And so now we have our autoencoder. We encode by finding C star, and we decode by multiplying C star by the dictionary D. Now, how do we get that dictionary? The cool thing about this is that we can learn the atoms that we need to use by simply having a neural network where we initialize random locations for our poles, which are parameterized by the real part and imaginary part, or by their absolute value, the magnitude and the phase. And so we can have very few of these numbers. For example, in this dictionary, I have only 80 parameters because we start with 40 poles over here, each of them having a magnitude and a phase. And then what we do is mirror image them across 4 quadrants. And because the dictionary has a structure, the only thing I need to learn is actually those parameters describing the dictionary. So now let me show you how we can use this for doing, for example, video prediction. Okay, so what we have done is we have a Diana autoencoder where the input are optical flows between consecutive frames. We encode that using the spark features I just described, and then we can decode that by multiplying C star with the dictionary to get optical flows, reconstructing what was the input, and then warp images to recover the actual frames. But we can also extend this. We can do prediction just by simply expanding the dictionary, adding extra rows. And this is very easy because these columns have a structure. Since I know the magnitude and the phase of each of these poles, I can just write down the extra rows in this dictionary. So once I have the expanded dictionary, I just multiply the sparse features that I obtain from the input times the dictionary, and that will give me not only the reconstruction, but also the predictions in the future. So we have done some examples here. I'm showing because of time, I'm only going to show a few examples, but this is, for example, on the Kitty data set where it was trained on the Kitty and tested on the Caltech. The model is very, very small because it has only 80 parameters and it runs really fast. So what you can see here is on the left is the ground truth video, and on the right, you're seeing the reconstruction 1 frame at a time. So as you can see, the quality is very sharp. They look very realistic and very similar, very close to the ground truth. If you go to metrics, then this was published in 2018. At that time, we were state of the art. And you can see that we obtained a very good SSIM and for both the Caltech data set and for the UCF data set. So we were pretty pleased with these results, but we wanted to look more carefully what we were getting. And when we did that, we observed the following. When we were predicting farther ahead in time, for example, 5 frames at a time, while the prediction looked nice to the eyes and it was getting good scores, relatively speaking, compared to the state of the art, we noticed that there was a severe lag in between the prediction and the ground truth. So if you look here, this zoom in of the, sorry, I'm checking the chat if somebody, okay, sorry about that. So I was saying, if you take here the ground truth against the prediction of the 5th frame in the future, you can see that the tire of the car is visible here in the prediction, while in the ground truth has already gone out of the field of view. And similarly, we can see a lot less of the track that's being seen here. And we can actually measure this fairly accurately by computing the optical flow between the ground truth and the prediction in both directions. And you can see that the optical flow is not 0. So clearly there was a problem and we wanted to figure out what was going wrong here. So looking farther on it, we realized that the problem that we were having is that we were having changes in the dynamics of the sequences that we were trying to predict. And that was causing lags because if you mix measurements from the old dynamics and the new dynamics, the old dynamics, which are no longer relevant, are poisoning your measurements, and we were having a fairly large lag in the prediction. And the question is, how was these dynamics, where were they happening, and why, what could we do about them? Okay, and so by looking at this, we saw that, first of all, because we were doing prediction at the pixel level, if for any reason that pixel belonged to an object that was changing dynamic, for example, say this track is moving on a flat level street and then suddenly starts going upwards in a hill, the optical flow here is going to change direction. And so there was a sudden change in dynamics. So that could be one source of changes in dynamics that we needed to address. The other one is that when a pixel change ownership from one object to another due to occlusion. So for example, if we look here at this red pixel, this pixel looks like belongs to the track. But as the track moves along, now that pixel belongs to this band behind it. And so in one case, we have the dynamics of the track, but then in a future frame, we have the dynamics of the car. And so these changes of dynamics was what is causing our lagging. So how do we fix that? Well, as I mentioned earlier, instead of just having one single linear time invariant system, what we can have is a set of linear time invariant systems and switch among them. And so the problem is now, how do we detect these switches and how do we model that? And the solution came from actually signal processing. What we did was we put a common filter at the latent space. If the dynamics are not changing, then what will happen is that the C vector, the latent features that we were having, should remain constant. And so what we can do is with this Kalman filter over here, we could compare what was the prediction that our network was doing and comparing against current measurements. And if there was a significant gap between the prediction and the actual measurement, then there was a change on dynamic and we could adapt on the fly and reinitialize. If there was no changes, we could use the new measurements to improve our estimate of dynamics and perform better predictions. And that's actually what we did. And so here's a diagram showing what I just said, meaning that what we do is we predict things using our Kalman filter. We compare against measurements. If we are within the covariance of the Kalman filter, then we know that this is just basically noise and we can use that to improve our estimates. But if there is a significant gap, then something has happened. And what we do is we reinitialize our modeling. Since the Kalman filter is the optimal recursive filter, that's actually the best that we could do in this case, because the dynamics in this case for the latent space is very simple. It's just constant dynamics. By the way, I don't mind if people ask me questions on the go. So if you have any questions, please interrupt me. Okay. So here's an example of that prediction I showed you earlier, where Diane was making significantly lagging errors after 5 predictions. Here you have the grand truth. Here we have a couple of competitive algorithms applied to that that sequence. This is the output of Diane, and this is the output of Kalman Diane or K Diane. And as you can see in this case now, the lagging that was here, that you could see the tire of the car is pretty much solved. Still, there's a little bit compared to the grand truth. It's still a little behind, but it's much better time. And actually, we can quantify this, as I mentioned earlier, by measuring the optical flow between forward and backwards, grand truth and prediction. And we call that the MMF, for mean maximum optical flow. And you can see that in Diane, that amount of gap was 20, but after doing Kalman Diane, that was reduced to 15. So that means that really the lagging went down. The other thing is that we tested with the LPIPS metric, that is basically a perceptual metric showing measuring whether the prediction looks realistic, and also with Kalman Diane, we got better resolution. So if you look at this, there's more sharpness. Another thing that was wrong with Diane is this division here on the window was not completely the right orientation, but Kalman Diane does better. So overall, this procedure resulted in better predictions and less lagging. Any questions about this portion? Yeah.
Perhaps oh, Brian has a question. Please unmute yourself, Brian, and go on.
And can you
You're far
speak
from the
louder?
mic. Yeah, probably you're far from the mic, Brian.
Yes, faintly.
I'm just noting some kind of distortion in the right of the image. I don't know if you can like.
All right. So the next thing that I wanted to talk about is doing classification. And in this case, I'm going to be talking about on the context of the tasks of cross-view action recognition. So here the task is as follows. We want to do action recognition, but during training time, we use videos, for example, from view 1 and view 2. But at inference time, we're going to be using a video from a totally different view that we have not seen before. And we want to be able to, based on this training data from the previous cameras and other, it could be other subjects as well, we want to be able to assign, for example, in this video, the label pick up an object. And so the problems here is that we're having these different viewpoints. Also, it's very possible that these views are totally unsynchronized. And again, there could be different individuals doing this task. And we want to be able to recognize something from an unseen view before. Okay. So we're going to be using, again, dynamics to help us in this task. And I'm going to show you how I can build some actually invariance into the representation, so that makes this challenging task easier. So the first thing I want to talk about is about the invariance with respect to the viewpoint. Okay, and so here I'm going to switch a little bit on my way of representing the dynamical system. In the previous part of my talk, when I was talking about Diane, I was using basically a transfer function representation where we have the poles of the system. Now I have chosen, because it's easier to understand what I'm going to talk next about invariance, a different representation where I'm writing the measurement at time k as a linear combination of the previous n measurements. So this is an autoregressive model of memory n. And the coefficients A are the basically the way that the system produces a new output based on the past. Okay. So these models, autoregressive models, have also associated with them what's called the characteristic polynomial, and that polynomial has the coefficients 1 and minus these coefficients A. And it turns out that the roots of this polynomial are actually the poles of the system, the same ones that we were using in Diane. So the reason I'm bringing this in is because with this formulation, with this representation, it's very easy to see that if these y coordinates over here are homogeneous coordinates, I can apply an affine transformation. I can apply a transformation multiplied by a matrix pi. And the transformed coordinates will have exactly the same coefficients A. Okay, so what that means is that these coefficients A, which are the coefficients of the autoregressive model and are also the coefficients of the characteristic polynomial that has as roots the poles of the system, are invariant to these changes in viewpoint. The same thing can be said about the number of poles, of course, because that's the number of roots that this polynomial has. So that has not changed. So from that, what we see is that the poles are affine in invariant to changes in viewpoint. The other invariance I want to point out, which is going to be key in this problem, is invariance with respect to the initial conditions. So again, I'm going to introduce one more different representation for the dynamical system. So here, again, I have the autoregressive model, but also we can represent the system by its Hankel matrix. And here, this Hankel matrix is a matrix that has constant diagonals in this direction, the off diagonals, and they're obtained by taking the measurements y and stacking them shifted by 1. So basically, you have your sequence and you use a sliding window, you move it by 1, and with that you generate the next column or the next row. And this matrix that has this structure is called a Hankel matrix, and it's a nice matrix because it's computed directly from the measurements from the data. And for example, people in system theory use this to identify the system. So one of the things that we can see is if this is true, and this is of course assuming no noise, we can see that this vector over here that's made of the coefficients A and the -1 that comes from taking the 1 over here to the other side is a null vector of this matrix H. That is, if we multiply this row vector times the Hankel matrix, we're going to get 0, because again, every measurement at time k is a linear combination of the previous n measurements, and all these coefficients that for the linear combination remain constant over time. So with that, now what we can do is by looking at yet another way of representing the system, in this case by using a state space, where we see a space, the state at time k plus 1 is just a matrix A times the state at time k. And the measurements of the observations that we have are the y, which are related to this internal state by a matrix C. Then by moving this along this equation over here, what we can see is that the measurements at time k is equal to the matrix C, the observation matrix, times a power of the state transition matrix A, power k, times the initial conditions x0. And if we do that for all measurements and we stack them together, what we can see is that this Hankel matrix that I have here can actually be factored out into the product of these two matrices, where the first matrix over here might be known by people that know about control. It's called the observability matrix that has the product of the observation matrix C and powers of the state transition matrix A. And this portion over here depends on the initial conditions and it's the trajectory of the state. But what is key about this equation is that on the left part, the factor here is independent of the initial conditions of the trajectory of the state. Depends only on the C matrix and the A matrix, which is the observability of the system. And so if we have a vector which is in the null space of the matrix H, that is omega times H is equal to 0, it is also true that omega times observability matrix is also 0. So we have that this null vector is a null vector of the Hankel matrix. It's also a null matrix of the observability matrix. And these matrices does not depend on my initial conditions. So that means that this null vector, which is this vector over here, is independent of the initial conditions. And that's very good news because that means that the poles, remember that the poles are the roots of the characteristic polynomial that has as coefficients these numbers over here, are going to be independent of the initial conditions. So that helps me because if my videos are not synchronized, they don't start at the same point, I still can use this approach because they will share the same poles. Okay, so with that knowledge, now we can present this two-stream approach for the task of cross-view, cross-subject action recognition. So we start with a sequence of videos. And we ran a pose estimator in 2D. There are very good off-the-shelf algorithms for doing that. We get the skeletons at each frame, and we do clip sampling. So that is, we take short sub-clips of the video, and we keep both the skeletons as well as the original images. That way, with the skeletons, we're going to have the trajectories of the joints of the person doing the action. So, for example, the shoulders, knees, elbows, etc. And that would pass through a dynamic stream that's going to use the dynamic invariance I just described to help doing the action recognition. While the second stream is going to just take the RGB frames and process that to give context. So we are doing the action recognition based on two things. We're doing on the motion of the joints, and also as well the appearance and the context around the person doing the action. Now, one key thing I want to stress is that if we use this is actually the dynamic space stream. If we use as input these clips and we pass that, for example, to a Diana encoder to encode like I was doing before, the latent features over here, which are sparse, this vector C is not independent, is not invariant to different initial conditions. It does actually depend on initial conditions. What is independent is which columns of the dictionary these features C are selecting from. And so what we need then is one more module that, looking at these features, can tell what are the poles being selected during this representation. So now with this binary code, then we can go through the classification. So we ran this two-stream network with a couple of data sets that are standard in literature for this problem: the Northwestern UCLA multi-view action and the NTU RGB plus D data set. These data sets do have 3D data, for example, and infrared, but we only use RGB data for our approach. And when we run our experiments and we compare against other approaches that only use RGB, we were able to improve performance by a significant amount by introducing this dynamics invariance in the skeletons. So for the Crossview problem, that means training from couple views and recognizing on the other view, we were able to improve performance by an 11% in this data set. And when we look at cross-subject, that means we want to recognize actions done by another individual. We were also able to improve performance for 0.2%. And what's significant also here is not only that this is a fairly large improvement in the RGB, but it's also that by introducing this invariance in the skeletons, we were able to close the gap that traditionally has been between methods that only use 2D data versus 3D data. So when you compare against the 3D skeleton methods, we see that our performance has closed the gap significantly. Before there was much higher difference between 2D and 3D methods. So this is for the UCLA method dataset. I'm sorry. This is for the other dataset, the NTU. It's a good improvement, not as significant as in the other one, but still 6% for Crossview and 5% for cross-subject. And again, there is a closing of the gap between RGB methods and the skeleton methods. All right. Any questions about that part? Because I'm going to move to my last application. No? All right. So the last thing I wanted to talk about is imputation and disentanglement, where we can use this way of representing videos that has physical meaning to do both imputation of missing data as well as disentanglement of different dynamics. So in the state-of-the-art self-supervised video decomposition, it's common to be able to, given a video with multiple objects, we can disentangle the position, the size, the appearance of the different objects, whether they are present there or have been occluded or missing. However, for dynamics, to separate the dynamics, it's not so clear how to do that. This portion, the position, the appearance, the size, the presence, they're fairly easy to interpret, and we have physical meaning for those, and we can look at the latent variables and understand. While for the dynamics part, traditionally, what people have been using are things like nonlinear recursive neural networks, and these are much harder to understand the physical meaning of what the network is learning. So in this portion of the last slides that I have for presenting today, I wanted to talk about an architecture that is inspired by human operators, where we are moving beyond just LTI systems that I just described for both the video prediction problem and also for the activity recognition. And now we have that nonlinearity that I was mentioning before, which is the input is assumed to pass through some nonlinearity. Then we have an LTI system, and then we have, again, a nonlinearity. So in this case, we're modeling nonlinear dynamics by transforming that into a map, using a mapping into a linear space where we have a linear operator, a Koopman operator, that can be used to advance or predict and model transitions over time. And the basic idea is that we can go back and forth between these two, the original manifold and the place where the dynamics are linear, using some nonlinearity mapping, which in our case, of course, is going to be a neural network. So here's the overall pipeline of what we have worked with. We start with a set of frames, Y1 to YT, and we pass through some neural network to get some deep features on which we can perform, for example, attention and tracking. And so we can separate the different objects. And what we have is a maximum number of objects. We can have less than that. Then this tracking will result in disentangled latent features where we have the pose. By pose, I mean the coordinates position of the different objects. We have a confidence latent variable that says whether the object is being visible or not. And we have a model of appearance, which is stochastic. Then what we do is with these disentangled features, which now we're going to force it, the network's going to learn in a way that they actually evolve over time using a linear operator, where we have now a Koopman operator that can be applied to the state, which is basically a concatenation of delay coordinates for both the pose and the inputs to the system. And with that, we can predict the following state. And then, of course, we can undo the nonlinear mapping that goes from the original space into the latent space by having basically a decoder. So this is an encoding portion. Then in the middle, we have a linear dynamical system that can actually evolve the state, and then we can go back to the original state. So with that, we can now not only create, reconstruct the input, as well as create predictions of it, but we can also tweak them and manipulate them to alter what we're seeing. So here I'm showing one example where what we did is synthetic motion of the MNIST, the digits, where the digits are moving using sinusoidal trajectories, and where we have artificially occluded the top portion of the frame. So the first 29, these are 64 by 64 images, and we have occluded a significant portion of it, 29 rows. And since the numbers are basically 28 pixels big, so it could be that the digit is completely obscure from the sequence. The sequence are 20 frames long, and we use the first 3 frames to learn. And with that, we are able then to predict what the reconstruct the input and also predict the future as well. So what you're seeing here on the right-hand side, on the very top row, is the ground truth of the output, the first 10 frames that we can predict. Actually predict 17, but just to make it the figure smaller, I'm showing only the first 10 over here. The DDPAE is state-of-the-art prediction reconstruction algorithm, and you can see that the reconstruction is probably blurry and it's missing some of the stuff. This is our method that we call KID for Kuhlmann interpretable disentanglement and descriptor. And you can see here that not only we are able to reconstruct and predict well, but we are also able to reconstruct things that are occluded completely on the scene. Okay, so what is the interpretation coming here? What we do is we look at the Kuhlmann operator, the linear operator on the latent space, and we look at the eigenvalues that of the transition of state transition matrix for the Kuhlmann operator. And here we are plotting what we see. And so the first thing that we notice is that many of the eigenvalues are very close to 0. And these eigenvalues, basically what it means is that they're not being used. We have a maximum number of eigenvalues that we consider, and so we can consider complex dynamics, but the system, the network learns by itself how many really needs. So the ones that are not needed are all pushed towards 0. Then we have these poles over here that are being learned. And what we're doing here is we took, for example, the pole here that it's on that green circle, and we move it along the circle by changing the face of the poles. Okay, and so when we change the phase, you see here on the bottom portion that we are able to alter the trajectory. This, again, remember, this is synthetic data that we have created, so we know that the trajectories are sinusoidals. And what we see here from is being learned is, first of all, that the network learned that indeed needs a pair of conjugate poles that are at the unit circle, and so we can have sinusoidal. And by moving them over here, we can change the frequency of that sinusoidal. So the other thing is that we play with is, can we change what happens if we change the magnitude of that eigenvalue? So these eigenvalues are on the unit circle, and we can move it towards the outside, making it unstable, or towards the inside. And what we can see here is that when we make it 1.5 R instead of 1, what we see is that the trajectory is such that it saturates, it's unstable, and it cannot go outside of the image, and so it gets out there. On the other hand, if we use an R equals 0, of course, the prediction is really bad, and 0.5 R is slightly better, but still, this is not the correct thing. So with that, I want to conclude by giving the following take-home message. First of all, dynamics carry valuable information. It's important to exploit it. And the reason why I believe strongly that it's useful is because by building into our architectures, we can design very compact and interpretable models. So we can understand what the network is learning, and also we can alter things and change, for example, the videos I was creating with the numbers. And moreover, the whole representation is differentiable, so it can be included in end-to-end trainable networks with no cost. So with that, I would like, on behalf of my team, say thank you for your attention.
Thank you, Octavia. Really interesting talk.
You're welcome.
Yeah, I mean, like interesting and also like I think refreshing, because most of the time these days is mainly about deep learning architectures. So I think that for the young community of the Latin people who might have, I mean, of those with electrical engineering background, LTI systems might sound
Yes.
related and refreshing for them. Oh,
yeah. So I'm not advocating, not to use deep learning. On the contrary, what I'm saying is that what I don't like is a black box deep network. What I like is to try to rescue all our experience that we have from before deep learning and from other disciplines like system theory, and see if we can put that into our networks to make them more compact, more interpretable, easy to learn and train. That's what I'm saying. So, I'm not saying not deep learning. What I'm saying is that instead of having black boxes, we can have gray boxes where we build into the architecture what we know about the problem. So that way the networks are more compact and understandable.
So, I mean, again, thank you. So I understood that clearly, like you were trying to actually marry both sides. Yes, I think that I agree that these kind of representations are more interpretable. So it's good. It's good to hear that. So I think that we are short in time. So thanks a lot. So I would like to thank Octavia again for having the time and sharing with us this. So Victor is actually, like I know from Twitter that he is an alumni from the UNAM. Is it the case?
Yes, I am.
Yeah. Now, like, well, he works. He did the PhD in the University of Washington, and now he's working for Microsoft Research, right? It's in a very interesting area because, like, I think that University of Washington, and he was probably like related with that kind of people, is close to the graphics community. So I think that Victor like did his PhD in computer vision, and now he's doing like really some technical stuff in machine learning. So I think that he has a really diverse background.
So yeah, thank you so much for the invitation. I'm very happy to share some of my research that I've been doing in my PhD and recently here at Microsoft. So thanks for the introduction, Victor. So at the beginning, I'm just gonna talk more about my background, like how is it that I reached to the state where I'm at right now, and then I'll finish with some technical stuff or problem that I really enjoy during my PhD and what I'm still working on in the current HoloLens research team. So yeah, actually, like Victor said, yes, I graduated from UNAM, the National Autonomous University of Mexico. I was born and raised in Mexico. I did my bachelor's in computer engineering, had a lot of fun there, learned a lot, and then decided to get my PhD in actually the University of California, Santa Barbara, with Professor Matthew Turk. Matthew was the eigenfaces person. So very impactful research that he had, and I had a lot of fun in Santa Barbara. Learned a lot, published papers. I was so new because I jumped directly from bachelor's to PhD that it took me a bit time to adapt to that transition, and also from country to the state. All those cultural changes actually influenced a bit, but I survived. I got my degree, and yeah, I learned how to do research by myself. So that's basically my education. I also want to share like some of my professional side. So after graduating from UNAM, I spent 1 year in the National Institute of Election, what it was called in Mexico before IFE. So I was there just a senior software engineer, where I was just helping maintain the big database, or the database of all the registry of voters in the country. And it was also helpful for me to get some experience, also some money before going to the PhD in California. So that was great. After graduating from the PhD, I wanted to try out academia. So I actually took a position as an assistant professor in the Department of Computer Science in West Virginia University. I spent there like 3 years. It was good. I learned how the academic life works as a professor as well in the US, where I was able to get some grants from NSF and also from NASA. But then I had a friend that actually met every CVPR, ICCV, or ECCV conference, and we always met there. And he was recently building a new team at Microsoft, and his name is Gang Hua. He at the time was at Microsoft, and he convinced me to join Microsoft at least for 1 year and give it a shot. And so I took a leave for 1 year from academia, experience what it was like at Microsoft, and decided to leave academia. So I'm now at Microsoft. At the moment, I'm a senior researcher there, and currently I'm working in the mixed reality org, where we basically work on the HoloLens. So we deal a lot with geometry and some deep learning as well. So with that, that's basically my background. And then I would like to tell you more about like a problem that I really like, even when I was a PhD, and nowadays it's still relevant, and I think it's coming back thanks to deep learning as well. And the problem is this image correspondence problem that is actually so fundamental for computer vision. And so let's recap what that is. So let's assume that I give you 2 images. Let's focus now on these images at the top, A and B. So what we want to do is actually associate pairs of pixels. In this case, we're depicting the same object. And what we want to do is actually recognize parts of this object, right? And this has a lot of applications that I'll explain in a second. Another way of computing correspondences is like when you actually give a semantic meaning to it. So for example, below I have 2 dogs, A and B. They're different, they're not the same object, but we semantically can actually associate pairs of pixels. For example, I know that the eye of the dog is here, but the eye on the other dog, which is not the same, also is there, right? So we can actually associate those pixels, and they can be useful for many applications. So this problem is fundamental, and I'm gonna explain more about like how we use this in geometry, because that's actually what we use a lot in the mixed reality org. So imagine that you have 2 correspondences in 2 images. So for example, here, when I say triangulation, if you have those correspondences coming from the same object, what you can do is actually recover the 3D point in the scene, right? So that is actually quite classical, but it can be so useful because when you start doing this, given multiple images, and when you start doing this pairwise, you can actually reconstruct the whole scene, right? Like for example, here, if you pass all the images from the Colosseum and you establish your correspondences somehow, you can actually recover the scene and also understand how the images were placed with respect to that object. So basically, you actually recover the entire structure and also the camera positions and orientations. Other applications can be optical flow. The correspondences, like are small, basically the delta of how the pixel is actually moving. To understand like motion, for example. Another application is image stitching, where you can actually find correspondences of the same object, and then transform one image into the other using some geometrical models in order to actually stitch the images together, and then have maybe panoramas and so forth, and many more applications. Okay, so this is why I'm very excited about this, because you can do a lot of things if you do this properly. Now, so how do you actually compute them? It's actually quite simple. This is basically, this equation that you see here is basically the nearest neighbor rule. And what this says is that you will detect features on the images. In this case, again, we're actually depicting the same object. If you want to find the correspondence for this particular patch that you see on the upper image, and then I have a reference set of features detected on the lower part of, on the lower image, then what we can do is that we're going to extract a patch around it, around that feature. We're going to encode it. And then basically this rule is telling us search on your database or your reference features for the closest or most similar descriptor in your database. And that's actually how you associate pixels, right? It is very simple. However, we can run into a lot of troubles, right? Because these objects can have like repetitive texture, and this rule is not robust to that. So you can actually have a lot of confusion in our system. So either you actually tweak your representation so that you're more invariant to those, factors that can influence the confusion in your system, like illumination, occlusion, viewpoint, etc. Or the other is mainly change the way you associate pixels somehow. But this is so simple that now with the use of deep learning, you can actually tweak this part, right? So this is why I was so excited in my PhD. And this whole theme motivated my entire thesis, actually, because I was so excited to reconstruct things, understand the scene, and create augmented or virtual reality applications. So what I did in my PhD was the following. This is when deep learning was not that commonly used, was that I grabbed this statistical theory that is called extreme value theory. And this theory actually, what it tells you are the models, the parametric models that you can actually use to model outliers or rare events, basically. And in order to model those failures of confusion when you actually use the nearest neighbor rule, what I did was the following. So if you analyze how you actually compute these correspondences, it's very likely you will get a lot of incorrect matches or correspondences. And that means that you can say that there's actually a process that can be captured by a statistical model over the distances, like when you compare your representations with certain distance and use that as a statistic, you can get a model for that. And what I did was to say, okay, now that I have a lot of these, then this means that if I have a good representation, like a descriptor, for example, SIFT, SURF, or a neural network based, then that means that actually the correct matches, the distances for those correct matches, can be seen as rare events of this distribution, right? So in the sense of distances, it means that actually those distances will actually live somewhere here that are rare, right? Like if you see this distribution, most of the mass is actually centered at some value and then it starts to fade out. But if you have a good distribution, a good representation, you will have another distribution for correct matches where all the distances will be 0, right? But that's not the case. You usually have like noise and other factors. So then you have some statistical noise that actually inflates your distribution of those correct matches. And that's actually what I was modeling here, where you have a process where incorrect matches have this distribution, but correct matches have another distribution that can actually be modeled with extreme value theory, and then sort of like detect them in a statistical way once you have this statistical formulation. So it's basically, I was just like trying to get a mixture model explained by these two distributions, and then get a classical detector that can tell you, oh yeah, looks like this is like a good match or a bad match. And that can be useful for many geometric applications, like for example, accelerating ransack, or just filter out like bad correspondences. And yeah, do a lot of those nice reconstruction and understanding how your camera is placed within the scene. So here I'm just showing two plots that I cut from my papers. If you're interested in more statistical mathematics, feel free to check them out. So what I'm showing here are just RC curves, where it's basically telling you the trade-off between how accurate is your predictor and how many mistakes or false positives or false alarms you're doing with that. So here I'm just comparing with the classical ratios that we use in geometry, like Lowe's ratio, which is also commonly known as SIF ratio test, other ratio that was not that popular, which is Brown's ratio, and then two methods that we proposed that actually use this statistical model. So the one that actually worked the best for us was this called in red. It turns out that a Rayleigh distribution is a special case of this extreme value theory, and that distribution actually helped us model better this prediction. And so, as the better your detector is, you will get a curve that is closer to the y-axis and then flat out, because that means that you will have all the true positives at any threshold in your detector phase, and you will have basically no mistake. But that's not the case, right? We're dealing with imperfect, noisy data. So every point here that you see in the curve is basically you're moving a threshold over your decision function, sort of thing, and you're actually getting a different performance point. So as you can see here, like this Rayleigh formulation actually allowed us to actually detect better all these bad matches, and actually, as we show in the paper, these weights or this confidence that we can get out from the statistical model can be so helpful to accelerate RANSAC and other estimators that are so useful for augmented reality, virtual reality, or robotics. Recently, we were exploring like semantic correspondences. We actually published this paper in CVPR 2021, where we follow a similar idea, but now we are not using statistical theories, right? Now we have deep learning at our disposal. And the idea was the same, like how can actually we predict the correctness of semantic correspondences given two images, right? So we propose this architecture, which is quite simple. Given two images, we pass them through a backbone CNN, we get feature maps, and then what we do is that actually we do this feature matching, it's basically everything against everything, and you will get a correlation map that is actually 3D. Given this correlation map, we use ideas from patch match, which is another interesting correspondence method that is actually quite fast. And you can get like ideas on how those patches actually match to others in your images. But then what we wanted to do here is actually learn a function that, given a section of your correlation map associated to a patch they're actually interested in matching, get a score, like a correctness score or prediction of if this is actually a good match, right? So every point in this correlation map is actually evaluating that. And so we learned a function that gives us that. We actually rank them, the correspondences based on these scores, and then plug that into patch match, because patch match also has a sampling structure that allows you to find the best correspondence in your set of two images. So we iterate that, and actually we show that actually works quite well. We were shocked that it actually worked. Simple idea worked quite well. On top of that, actually, we were able to reduce the complexity of examining all the entire correlation map to do these predictions, as opposed to other networks that are called ANCNet and GSF that are also fairly recent. So we were shocked to see that actually, besides accelerating the matching process, we also improved the accuracy of the matching. So here I'm just showing some qualitative results, because the results that we have in the paper are big tables, and I don't have enough time to discuss them. But basically, what I'm showing here is like results on this SPARE 71K dataset, that despite having like different viewpoints, scales, and objects, what you see on the top are like query images, where the orange dots are the features that we're interested in matching on the images below. So for example, here on the bus, you will see that this orange was mapped to this part of the bus here, and this like green circle is technically telling you like a threshold of error. And you can see that actually our method is quite good. It's quite accurate. And so we were very happy to see this. So if you're interested, feel free to check out my paper. And just to tell you things that we're excited to explore, obviously, is to improve representations that can be invariant to many factors, like illumination changes, viewpoint, rotation, and so forth. But we're also interested in like see if we can actually include information from other modalities like that we can have access, like for example, inertial sensors that can give us the upright direction in an image, so that perhaps embed that context in the representation in using neural networks. So those are the things that I'm excited about right now for this problem, which are useful in geometry. And just to finish, I just want to give you this quote from Professor Takeo Kanade, where he was asked, like, what are the three most important problems in computer vision? He answered, correspondence, correspondence, correspondence. So with that, I finished, and thank you so much for your attention.
So I will finish if you want. Thank you a lot, Victor, for your presentation. Very inspiring. I didn't know you until actually some people started, the people from Orlando started promoting your profile on Twitter. I learned that actually from Mexico. So I'm really
Nice.
to showcase in Mexico that we have Mexicans working Microsoft HoloLens and so on. So it's very, very, very inspiring and really nice.
Thank you.
Because you can show that how things that were like, I mean, 20 years ago, people were doing this, 10 years ago, were people doing this, and it still is important and it's still relevant. So
Yeah.
thank you for your presentation. Yeah.
Thank you.
Claudia, thank you a lot for accepting this invitation. I don't know, Danielle, if she already has access to share screen.
Let me check that. 1 second.
Yeah, so thank you, Claudia. Yeah, you can hear you if you want.
Yeah.
You introduce her a bit better than me.
Yeah, so I mean, I'm really excited to introduce Claudia. Claudia is actually a roboticist. So, and she was hesitant, like, oh, but are you sure that my talk will fit for a computer vision audience? And I mean, my answer to her was like, in Latin America, I mean, I don't think that it's a good approach to tackle AI in silos, as we were like, for example, oh, computer vision, machine learning, NLP, robotics. I think that now it's the time that, I mean, actually the technology has evolved, that we talk together. And I think that it's, I mean, really, we are really pleased to have you here, Claudia. So
Yeah.
take it.
You know, just a cultural note, here in Mexico, most people doing computer vision are in robotics. So, yeah. Yeah, so thank you. We're really looking forward to hear you.
Thank you so much for having me here. I'm super excited to share with you my work. I think I agree with what you just said. Actually, I'll talk a little bit about how perhaps the fields are converging. And this is how I feel like there are venues in which computer vision will converge with robotics. And we are getting actually to that point now with the maturity of the fields in which they are actually able to work together. Anyways, yeah, so my name is Claudia Dorpino, and I actually just moved to media, and I'm started as a research scientist there. But the work I'm discussing today is part of my postdoc at Stanford in the Stanford Vision and Learning Lab. And in these 15 minutes, I'll talk about learning for human-robot interaction and bring up some challenges for computer vision that are key for advancing human-robot interaction. So there is a broad variety of important applications in which human-robot collaboration has the potential to improve our lives. And they could perform side-by-side manipulation at home. They could navigate moving around people, for example, at homes, malls, airports, supermarkets, hospitals. They could also learn from humans how to perform human activities in our environments. A second type of collaboration is remote manipulation, in which a human can directly control or supervise a remote robot. And this can be useful at home, manufacturing, and also in disaster response sites. All these scenarios can benefit from robots that can learn to interact with humans in different capacities. Unfortunately, we are actually very far away from realizing robots that can fluently collaborate with humans in these tasks. But this is a challenge we are up to. So I'm personally interested in exploring how we can better leverage simulation for human-robot interaction, or HRI research. So recent work in simulation environments for robotics have been focusing on increasing the visual realism compared to previous more abstract scenes, like this one here on top. You see like all these abstract colors, it's not a real environment, and so on. And nowadays, there are a number of simulators that are coming up online from both academia and industry, in which we're trying to increase the photorealism of the environments, as well as the realism of the objects and the distribution of objects in these environments. Now, for HRI, we will also need to increase the realism of simulated agents. So not only how these static environments look, but also how agents within the environment can behave. This can be used for several types of interactions, either to immerse humans in simulated environments and collect demonstrations of human activities, or to have human virtual agent interaction for training of different policies. We can also have large-scale simulation of interactive scenarios, such as an entire office floor with simulated pedestrians, or maybe entire home or apartments scenarios. And actually, this is a really good first domain to explore robot learning tasks that involve interaction, but that occur within simulated but realistic human environments. So today, I will start by talking about this particular application of mobile robotics around people in simulated but realistic human environments. And concretely, I'll be talking about our work on using reinforcement learning for social navigation in constrained pedestrian environments. So navigation around pedestrians have been typically studied in spacious areas where there is ample space for the robot to move around the pedestrians. However, typical indoor environments exhibit spatial constraints that make navigation around pedestrians more challenging. Learning to navigate socially in these indoor spaces, such as home, offices, and stores, is a necessary step in bringing robots into our daily life spaces to do tasks with and around humans. Now, these constraints environments limit the mobility of the robot because naturally it's more difficult to maneuver around the moving pedestrians in smaller spaces. Now, these constraints form basic geometric elements that repeat across layouts, such as corridors, intersections, and doorways. These basic elements are important not only because of their geometry, but also because of the patterns of interaction that emerge as a consequence of that geometry, such as moving towards the side on a corridor to give space to another person, or going through a door while there is another person on the other side waiting. Now, real indoor layouts combine and compose these basic elements for both the geometry and the interaction patterns, and this is an insight that we are going to leverage in our work. First, here are some related approaches for social navigation tested in indoor environments. First, we can use a motion planner alone. Having an explicit plan is interpretable, but planning often results in the robot freezing problem, which I'll show you a video of later. It also requires manual designs for social behaviors and parameters, making it very challenging to cover many social situations. Then the combination of imitation learning and planning helps learning social behaviors from human demonstrations, but it requires extensive data collection, which can be very costly. Previous work found that robot behaviors are too limited to examples seen in the demonstrations, not adapting well to new interaction scenarios. This motivates the use of reinforcement learning, in which the robot collects its own data. However, we found that using reinforcement learning end-to-end resulted on a sample complexity that increases with the layout size and geometry, not really focusing on the local aspects of social interactions, where the short-term interactions in the vicinity of the robot are really the most important. Now, in order to obtain the benefits of RL, but avoiding the increased sample complexity, we combine reinforcement learning with a motion planner. And this enables the planner to reason about the long-term trajectory, while the RL component is focused on the short-term local interactions of maneuvering around the pedestrians. To implement our approach, we needed to design first a simulation environment, which I'll describe first, and then I'll cover our approach to policy learning and then experiments and results. So learning for tasks that involve multi-agent or human-robot interaction demands the development of new types of simulation environments that go beyond the typical robotic single-agent learning. We developed a multi-agent simulation environment based on iGibson and Bullet as physics engine, and it includes simulated pedestrians with very basic interactions. This video here shows a simple walls world with a number of moving pedestrians and a robot. In order to simulate pedestrians, we use the open source library for optical reciprocal collision avoidance, also called ORCA, and here I describe some of the behaviors it enables. So ORCA guarantees collision-free motion for all the agents if they are all following the same protocol. And it does this by computing the desired velocity per time step for each pedestrian by solving a linear program with the known velocities of all the other agents. So clearly you can do this to run the simulation. You wouldn't be able to do this in real life to get, for example, an ORCA robot. That wouldn't be possible. Our simulation is instantiated as follows. Start and goal locations are sampled for all agents. The simulator pedestrians use ORCA to navigate to their goals. And if the pedestrian reaches the goal, just a new goal is sampled to keep the simulation going continuously. As a robot platform, we use this differential drive robot Jackrabbit, which is a platform that we had at Stanford. So note that this simulation actually includes interaction. The pedestrians believe that the robot is also following this ORCA protocol, and therefore the robot's velocity is taken into account for pedestrian decision-making. Now the robot is instead following its own policy, of course, which also reacts to the presence of the pedestrians. So this results on all agents considering each other, achieving effectively a cooperative behavior inside the simulation. Now for the policy, we propose this architecture. It receives guidance from a motion planner through a global plan, giving us input to the policy as a sequence of waypoints. The action space is linear and angular velocity for the robot platform, and we train this policy on the previous simulation environment using sub-actor critic, which is an off-policy continuous space deep-parallel algorithm that optimizes not only for the expected cumulative reward, but also maximizes the entropy of the policy, encouraging more exploration effectively. We use a combination of dense and sparse rewards terms. The robot is penalized for collisions with pedestrians or static obstacles. It is rewarded by following the waypoints and achieving the goal, of course. So note that in the absence of pedestrians, it is enough to strictly follow the waypoints to get to the goal, right? Here, the red waypoints. But when the pedestrians are moving, the robot naturally might need to deviate from these waypoints. So we assign a reward for each of the waypoints, but given certain threshold around the waypoints so that it is still rewarded by following them closely enough. We also have a small time step penalty to encourage the robot to minimize time as possible. Now, the point here is, or the key point here is going to be in what layouts we're going to train the robot. And based on the insight that typical indoor environments have combination of basic elements, we explore using a compositional principle in our training regime. We train the agent in a small number of simplified templates, such as corridors, intersections, and doorways that are made of straight walls only, like the ones shown here on top, and explore two types of generalizations to unseen environments shown below. First, testing in more complex layouts, still wall swirls, but with the composition of the basic elements. And second, testing in environments that are representative of real human indoor environments, such as an apartment, for example. We simulate this by using a mesh from a 3D reconstruction from a real indoor space. We tested this idea by training in different subsets of simplified layouts. And we found that, in fact, generalization to a more complex layout achieves higher success rate when we train in the basic templates that are relevant to the target one, like the ones here on top on green. If we train in a different combination of the simplified templates that are less relevant to the target, then the success rate, average success rate of the generalization drops significantly. We compare our approach with using planning only by using the planner available in the ROSNAV stack. So here we see a video of how the planner adapts to the moving pedestrians, being the plan the green line there. So this green line is continuously changing the side of the corridor as the pedestrians are moving. This is how the planner is working. Now, if you see that same behavior in this other example, we can see how the robot freezes because it is unable to find a feasible solution in the time it has to replan while the pedestrians are moving and plans quickly become obsolete. So this is what's happening here right now, and this is commonly known in this research field as the robot freezing problem. And this is basically why we don't use planning alone. Instead, we combine it with learning, which is the proposal here. And this video at the left shows our proposed policy in action. We compare it with the planner with an increased number of pedestrians, and we find that while both decreased performance with higher density, the combination of planning and learning had higher performance in all cases. And really, failures have different reasons. For planning, the problem is the robot freezing problem. For policies, actually, that the robot doesn't freeze, but it has collisions, which I know it sounds pretty dangerous. But a real deployment will, of course, have an additional LiDAR and force safety stop, which we didn't include here to analyze the underlying performance. Additionally, we believe incorporating prediction of pedestrians' trajectories will help diminish the probability of collisions. And there is a lot of related work that has attempted this in open spaces. It is still a challenge to do it in indoor constrained spaces. This is the second type of generalization that is enabled by our multi-layout training approach with simplified templates. This is really a result I was very excited about. Here we train in the same set of simplified layouts, but now test in a previously unseen novel 3D reconstruction of a real, in this case, an apartment. The robot learns interesting behaviors, such as waiting and back up to negotiate the space with the interactive pedestrians. This is very quickly, just another example. We also tested in a reconstruction of a supermarket where the pedestrians and the robot maneuver around each other here in the L. They kind of find each other, negotiate the space, and keep going. Okay, so far our results are in simulation only due, well, mainly to the current limitations of real testing. However, I would like to show you here the target platform. This is Jackrabbit at the Stanford Vision and Learning Lab. So in terms of potential for sim to real transfer, we have previously tested real deployment of policies with the same action space, linear and angular velocities, and obtain smooth behaviors like this one in which JR is following me. Somebody's gonna cross, he's gonna slow a little bit and keep going. So while in simulation, we let agents have access to privileged information, such as the position of the pedestrians, on the real platform, we must obtain this information from raw perception, LiDAR, depth, camera, stereo vision, and so on. And this is where we need a lot of help from computer vision. This is a video, for example, obtained from the JRDB dataset, which I encourage you to check out online. This is data taken from onboard the Jackrabbit platform that I just showed you, and it has been labeled for all 2D and 3D positions of the pedestrians. So as I said, in simulation, I get directly the position of all these pedestrians, right? When you launch this on the real robot, you need to get these positions from this type of data. And while there are methods that can do this with good percentage of accuracy, it's not really a solved problem in terms of sometimes missing track of the pedestrians or maybe people going in and out of the frame, changes in visibility and so on. So really pushing towards highly accurate methods to recognize and track the pedestrians around the platform while the platform is moving in real and crowded environments is something that is really needed for real deployment of these platforms. Now, lastly, 30 seconds more. A next step also in visual perception is to include semantics as well. So in the work I show you, we only use LiDAR, but there is a limited number of things that we can learn from LiDAR. For example, it's really hard to obtain the semantics or know, for example, things is a corridor, there is a door, or there are these type of objects, and therefore there are pedestrians' behaviors that are highly correlated with specific semantic elements in the environments. So if we could have this in real time from raw perception, is something that we could greatly improve the performance of our learning algorithms when not in simulation, but deployed on real life. With that, I'll conclude the talk, and it would be great if you have any questions. Again, thank you so much for having me here today.
Thanks a lot. So maybe we have time, but for a very short question, if anyone wants to unmute and ask it. So, I mean, now that you, like, for example, I guess that you mentioned recently, that you just moved to NVIDIA. So I guess that I mean, how do you see that path forward, like towards, I mean, working more on the simulation aspect, making it like more realistic? And maybe if you can maybe kind of give us a hint or a gist of who,
Yeah,
I mean, what
absolutely.
your
So
plan.
I'm definitely very excited to continue this line. I think one of the key points that NVIDIA technologies will enable for this type of research is the heavy use of simulation, right? Both for the physics engines and also for the rendering. So in the type of work that I showed, as I said, there is only LiDAR. But I'm really looking forward into moving human-robot interaction research now into fully fledged simulation that can actually enable, sim to real, perhaps. This is a topic that is heavily studied in robotics for single agent, but what about when we have, humans around the robot platform, which is, to be honest, most of the realistic applications that we can aspire in the open world, other than industry or like manufacturing, where robots are separated from humans, right? So I'm definitely really excited to continue to try to explore how we can enable, real simulation for HRI research.
Great, thank you. Let's continue with Iván. Thanks a lot, Claudia. So Iván, can you share the screen? I see you in the. I see your face.
Let me check.
Yeah. So in the meantime, let's take the opportunity to introduce Iván to those of you who don't know him. So he's an assistant professor actually in the Department of Computer Science of the University of Chile. So he's actually, I believe, from Peru. And he did his PhD in the University of Chile, and he was a postdoc in the University of Constance. I believe that sounds like a bit German,
Yes.
or that area, right? So I'm really looking forward to hear about Iván, who is working in LATAM and who will share with us some of his experience using computer vision and combine it with reconstructing the pre-Columbian culture heritage of our continent. So thanks a lot, Iván, for accepting the invitation.
Yeah, thank you very much for the invitation to the organizers of this workshop in ICCV 2021. Well, I am Iván Sipirán. My name is Iván Sipirán. I work on shape analysis for cultural heritage applications, basically applications of structure discovery and also three-dimensional correspondences in 3D data for trying to rebuild and reconstruct archaeological objects in Latin America. So let me explain first what is the subject, what is the field in which all these topics are in. So let's suppose we have an object, a real object. Okay, so in this case, I will use an example for the Eiffel Tower. So basically, we have a real object located in some place, and we have some concept about this object. And then what we can do is, for example, taking a photograph of this object, and we can have a first computational representation of this object. It's basically just pixels that represents the color of the real object. So what we can do in one of the first big area of computer science, which is the computer vision, what we can do with this in this area is just to build a three-dimensional or reconstruct this object using image processing and image analysis techniques. So the idea of computer vision is to extract information from the images to reconstruct the real world. And also we have another area, which is the computer graphics area. And the computer graphics area takes three-dimensional data, which is the computational representation of three-dimensional data, and converts it again to an image. So through rendering processes or something like that. So in some point we have these two big areas connected, because these two areas depends on a very specific kind of data, which is the three-dimensional data. The three-dimensional data is the ultimate goal of the computer vision and is the input for the computer graphics topics or computer graphics techniques. So my research field is split in two subfields, which is the geometry processing. Basically, the geometry processing is how we represent, manipulate, or enhance the three-dimensional data to have a better representation in the computer. And the shape analysis is about the knowledge extraction from 3D data, which is basically more related to computer vision, right? You have a three-dimensional representation, and you want to use machine learning, deep learning, or something to extract knowledge from this information, from this data. Okay, so one of the nice thing about this field is that we can have contributions in any of these two areas. So basically, we can publish papers in computer vision venues and also in computer graphics venues. So that's good because we have a lot of more options if we want to make these contributions in computer science. So let me talk about what is my short experience as researcher and also the contributions in this field from the beginning of my career, which is basically my PhD studies in the University of Chile from 2009. Basically, in this period of time, we did many contributions about the selection of features and also the correspondence problem in three-dimensional data. You saw the talk of our previous speaker about how we can do all these things in images, but in this case, in the shape analysis field, we want to do correspondences matching, but not in the images, but in three-dimensional representations. So for that, for example, we need to select information. We need to select some points, and we have a good algorithm to do that, which is the Harris 3D algorithm. This is one of the first contributions of my PhD studies. And then we compound many different algorithms to do, for example, region detection, shape segmentation, and also for the matching and retrieval, which was one of the nice contribution that we published in ICCV 2013. So basically, in all this period, what we did is basically just a basic research about what is the capabilities of the algorithms to produce some semantic information about 3D data and to give some reasoning to the algorithms about 3D data. But one of the main lessons of my PhD was that in this period is the right period of time in which you need to build your network of research, because everything people that you knew in this period will combine you with the rest of your career, and basically you have to show to others what you are doing and what you are pursuing in your career. So this is something also that I recommend to my students, to build your network and also to connect with people, because you will remain in that community, and you have to know what is the important groups, research groups in your community and everything. So another decision that maybe one person that is finishing this PhD is, okay, I go to academy or I go to the industry. So probably it's a very difficult decision. But I think something that you have to do if you want to make a good decision is, what do you want to do? This is not about the rest of people. This is about you, about what you want to do, what you envision yourself in 5 or 10 years. If you want to do research in a more basic stuff or something like that, maybe you want to go to academics, or if you want to make some things working, you probably go to industry. So I prefer to go to the academics. So and this was basically just a decision because I had a proposal for doing a project in which we wanted to apply all the basic research in a real problem, and this problem was the conservation of archaeological material. And in this project, the Precious project, was basically just to take archaeological objects, broken archaeological objects, to use high-tech 3D scanners to have three-dimensional representation of the fragments, and then to compose and reassemble the objects, and also to complete the objects using some kind of prior information, prior geometric information, to have the completed and the real object as if the object were built right now. So we did some interesting contributions in this field, basically surface analysis, and also some contributions in the matching of symmetry correspondences, and we did some important contributions also in real sites. For example, we did this reconstruction of a embrasure in the Trondheim Cathedral in Norway. So we did some important work. This was applied research, but in the core of this research was a very strong basic research, for example, for the physical theory analysis of surfaces, three-dimensional surfaces. So after the postdoc, we had to make also some decisions. So in my case, I decided to come back to Peru, because I thought I was ready to push all my knowledge in this area in some more local information, and also in some more local problems. Okay, but one of the first problems was that I struggled to search funding in Peru, because in Peru we have a weak funding system for research, and also it's very difficult to get funding for basic research. So what we used to do is just to use a pretext task. You know, you have to make basic research, but you have to propose some application and just to apply this into a real problem, and some problem that you can see that this research is working. So basically, we started to do some more basic research about the symmetry analysis on surfaces, but applied to the cultural heritage applications in Peru. And you know that Peru is a very the resources of the archaeological sites in Peru is huge. So basically, this topic was real important for not only for us as academics, but also for the society. So that's why, for example, we received an award from the Fraunhofer IGD Society in Germany about our research for the impact on society in 2018. And also we received some covering in the press because we built a system, which is the SimArch system, that is working in the Larco Museum. If you know, Larco Museum is the biggest private collection of archaeological objects in Lima, in Peru. So yeah, and also in the last years, we have turned our research to the deep learning topics. So basically now we have experimented with, for example, some generative models for doing reconstruction of three-dimensional objects, and also now we are working on a more geometric neural networks for doing some things about point clouds and also three-dimensional meshes to complete three-dimensional objects, also working on a local museums in Peru. In August 2020, I moved to the University of Chile. So now I am professor at the University of Chile, but I am connected to the research in the local museums in Peru, and also we are doing research here in Chile in these topics. So yeah, just to give my final remarks, in my experience, one of the first points is that research is social. So we have to connect ourselves with peers, and also maybe this is a good opportunity to just not connect with people in our areas, but also to connect people with another fields also in LATAM, because we need to enhance all these nexus. Okay, and also I want to highlight that we need to do some activism in LATAM. We need to do this activism because we have to push to, for example, decision-making persons in the governments that this is an important area, and that we need fundings, and that all these advances that we are doing in these researches are beneficial for the society. And I think this is something that we also have to highlight and also to make to the rest of the people, not only in our community. So thank you very much for inviting me and also for having me here. This is my webpage and my contact. So please, if you have any question, I am open to answer.
Thank you, Iván. I mean, I think that it was really interesting and really, I mean, like you really connect, I mean, a bit of yourself with research, like how is it in an inspiring way. So I really like it. Thanks.
Yeah, I also want to say that thank you, because this, you know, I don't know in other countries in Latin America, but we always say that, for example, in Mexico, we say that we care a lot about heritage, right? Like we come from the Aztecs, but unfortunately, a lot of time, oftentimes, it's people from other countries that actually rescue the heritage of our nations, right? So it's important to show that actually people from another country, you're doing research and you are doing impactful research to preserve and study the heritage of Peru. So this is really inspiring, and I think it will help other students to pursue similar career paths.
Yeah. Thank you very much.
Thank you. So I mean, like if anyone wants to ask a question, perhaps, I mean, I feel free to do it. I mean, like, just to let you know, right now we will have I mean, like we were in the break session. Right after we will move to the poster presentation. So I really encourage everyone like to go to Gather Town, talk to the researchers who really, I mean, like took the time and want to share their research with others in Latin America. Please, I mean, talk to them. Let's see if you find something interesting and possibly some collaborations emerge.
Yeah.
Thanks,
also,
everybody.
I also want to note that for all the chairs that are in the session, don't forget to talk with at least three presenters to try to find the best poster presentation, because we have a prize for best poster that we already selected. We have a best prize for best doctoral consortium presentation that we already have. So now with the chairs will be talking with the presenters to try to find the best poster presentation. So thank you a lot. See you in the poster session.